live inside clouds that are very turbulent, while others look like they're in clean environments. From the properties of this news signal, we can say that around this source there is a cloud of plasma that must be extremely turbulent. You hear that? That's a cloud of plasma. The astronomers hope to catch additional bursts from the periodic FRB, which can help to refine their understanding of its source and of neutron stars in general.
I'm also, of course, reminded of, the dark forest. Like,
oh, yeah, yeah.
This is one of the ways in those books, in those stories, the three-body problem, that a civilization can speak to the entire universe is by pulsing a star. Mm-hmm. And if you do it with enough energy, or if you find the right resonance, basically in the series, there's this idea that if you beam a specific strength of signal at a particular star at the right resonance, the star will respond by magnifying it enormously, and it can come out looking like a huge radio burst coming from the star, but the star is actually just picking up your signal, massively amplifying it, and then pulsing it out in every possible direction. But that's your civilization being loud.
So I wonder if there's like a lot more data in the signal.
Yeah.
That we just can't.
That's what I'm saying is like it's like a one-time pad, right? You would need to know how to decode it.
It's wild.
Yeah. But if you can do that, it is one way to speak to the entire universe. It would take a long time.
Yeah.
But if you have long-term plans, or you don't care how long it takes, and you can pulse a star like that, then you will know eventually that everything in the universe basically will be able to see the signal if they're looking.
Yeah.
Yeah.
It's cool to I just this kind of stuff, I just love it because it's like, even if we did ever discover all the laws of physics exactly as they are,
yeah,
there's still such an enormous complicated
their interactions are complicated. Yeah.
Infinite number of possibilities of these things coming together and interacting, which can still create these vast mysteries out there.
Yeah.
So it's so cool.
And that thing that they just saw happened, but like probably before the Earth was here, right? That's the other crazy thing about it. Is
how
like,
far away was it?
Well, maybe it was 2 or 3 billion light years away.
It just says billions.
Right.
I don't know.
But still, it's just like the event took place before life on Earth.
Yeah.
Yeah.
Long time ago.
Yeah.
Long time ago.
So whatever made it is long gone.
It's wild. Man, yeah. That is interesting to think of. Okay, so moving on, something a little closer to home here. This is from phys.org. Scientists propose solution to long puzzling fusion problem. The paradox startled scientists at the U.S. Department of Energy's DOE Princeton Plasma Physics Laboratory, PPPL, more than a dozen years ago. The more heat they beamed into a spherical tokamak, a magnetic facility designed to reproduce the fusion energy that powers the sun and stars, the less the central temperature increased. So taking out the inside, the middle of that sentence, the more heat they beamed into the tokamak, the less the central temperature increased. Big mystery. Normally, the more beam power you put in, the higher the temperature gets, said Stephen Jardin, head of the theory and computational science group that performed the calculations and lead author of a proposed explanation published in Physical Review Letters. So this was a big mystery. Why does this happen? Solving the mystery could contribute to efforts around the world to create and control fusion on Earth to produce a virtually inexhaustible source of safe, clean, and carbon-free energy to generate electricity while fighting climate change. Fusion combines light elements in the form of plasma to release massive amounts of energy. Through recent high-resolution computer simulations, Jardin and colleagues showed that what can cause the temperature to stay flat or even to decrease in the center of the plasma that fuels fusion reactions even as more heating power is beamed in. Increasing the power also raises pressure in the plasma to the point where the plasma becomes unstable and the plasma motion flattens out the temperature, they found. These simulations likely explain an experimental observation made over 12 years ago, Jardin said. The results indicate that when designing and operating the spherical tokamak experiments, care must be taken to ensure that the plasma pressure does not exceed certain critical values at certain locations in the facility, he said. And we now have a way of quantifying these values through computer simulations. So the findings highlight a key hurdle for researchers to avoid when seeking to reproduce fusion reactions in spherical tokamaks. These devices are shaped more like cored apples than more widely used donut-shaped conventional tokamaks. The spherical devices produce cost-effective magnetic fields that are candidates to become models for a pilot fusion power plant. So this is cool.
Yeah, that's cool.
And then they have some diagrams here that are like, I guess it's like showing the like his basic theory on what's happening in the plasma and how it flattens out and I guess I don't know. It's almost like I'm kind of equating it to like something's going on akin to boiling. It's like when you're trying to heat
regulating
water,
its own temperature.
Yes.
Yep.
It starts to do some kind of convective motion or some kind of action.
Yeah.
That sheds the heat.
Makes sense.
Yeah, that's what came to mind to me. Because you can keep beaming heat at water, but it's
fusion power would be amazing.
Yeah, that would be great.
Yeah.
So glad they're working on. I got another one, but I mean we're already over time here,
Yeah.
so
Yeah.
we can do it next week.
All right.
It's about dreams. All right. Well, we'll be right back, folks.
We will.
Now, it's obvious to everybody that the phenomena of the world are evidently irreversible. And that I mean things happen that don't happen the other way. You drop a cup and it breaks. You can sit there a long time waiting for the pieces to come together, come back into your hand. If you watch the waves breaking at the sea, you stand there and wait for the great moment when the foam collects together, rises up out of the sea, and falls back further out from the shore. It would be very pretty. As a matter of fact, the demonstration of this in such lectures is usually made by having a section of moving picture in which you take a number of phenomena and running the thing backwards and then see all the laughter. The laughter just means this ain't going to happen in the real world.
And we are back, ladies and gentlemen, Brothers of the Serpent podcast, for the, fourth installment?
I don't know. I haven't been numbering them.
The Feynman lectures on the character of physical law. And it's like the fifth lecture in the fourth episode or something.
Something like that. This one is the distinction of past and future. And I'm actually hoping that we're going to get through this one and then probability and uncertainty as well. And then we'll finish up the series with Seeking New Laws next week.
Yeah.
So continuing with what Feynman was saying there, the laughter just means this would not happen in the real world. But actually, that is a rather weak way to put something which is as obvious and deep as the difference between the past and the future. Because even without an experiment, our very experiences inside are completely different for past and future. We remember the past. We do not remember the future. We have a different kind of awareness about what might happen than what we have of what probably has happened. The past and the future look completely different psychologically, with concepts like memory and apparent freedom of will. Right? Apparent. He questions free will. It's only apparent.
Well, yeah, because we're just masses following the laws of physics.
That's right. We're just very complicated machines, right? In the sense that we feel that we can do something to affect the future, but none of us, or very few of us, believe that there is anything we can do to affect the past. Remorse and regret and hope and so forth are all words which distinguish perfectly, obviously, the past and the future. Now, if the world of nature is made of atoms, and we too are made of atoms and obey physical laws, the most obvious interpretation of this evident distinction between past and future, and this irreversibility of all phenomena, would be that some laws, some of the motion laws of the atoms, are going one way, that the atom laws are not such that they can go either way. There should be somewhere in the work some kind of a principle that, and I'm not sure how to say this, maybe we should have listened to it, that uxels only make wuxels is how it's written. UXLES only make WXLES. WULES. So he says, yeah, uxels only make wuxels and never vice versa. And so the world is turning from Uxley character to Wuxley character all the time. And this one-way business of the interactions of things should be the thing that makes the whole phenomena of the world seem to go one way. But we have not found this yet. That is, in all the laws of physics that we have found so far, there does not seem to be any distinction between the past and the future. The moving picture should work the same going both ways, and the physicist who looks at it should not laugh. Let us take the law of gravitation as our standard example. If I have a sun and a planet, and I start the planet off in some direction going around the sun, and then I take a moving picture and run the moving picture backwards and look at it, what happens? The planet goes around the sun in the opposite way, of course, and keeps on going around in an ellipse. The speed of the planet is such that the area swept out by the radius is always the same in equal times. In fact, it goes just exactly the way it ought to go. It cannot be distinguished from going the other way.
Now, why does he use that example? Because if you think of like, well, let's say this comet comes in and it falls into the sun.
Yeah, an impact would be, you would obviously see that couldn't go the other direction. It seems like, right? But what he's saying is even with that event, if you zoom way in.
Yeah, of course. Everything's obeying the law.
Right.
Even if it's
then there's nothing
backwards.
that's happening that's wrong. But I agree, like, when I first read this, I was like, yeah, okay, for an orbit, if you reverse it, you wouldn't even actually be able to tell that it isn't correct
right.
time-wise. But for something like an impact or dropping a cup, it's immediately obvious that it can only go in one direction, or that it only ever does go in one direction. But if you looked at it on the molecular scale, you wouldn't be able to tell.
Right. Yeah. But okay. I was just thinking specifically about the laws of gravity, that if you were looking at it on the small scale, but you knew that the sun's mass and you knew all this whatever, and then you see this thing just moving away from the sun.
Yeah.
And I guess it would start out going really fast and have escape velocity and then slowly slow down as it got further away and it would look fine. Is that what would happen?
Yeah.
Is terminal velocity escape velocity?
Well, let's take a...
do you know?
No, terminal velocity is not escape velocity.
So
terminal velocity is about usually like atmospheric interference.
Oh, okay. Gotcha.
Right. So like...
I'm thinking of like, yeah, so anyway, I was getting in the weeds, but if this thing is going really fast and then it's pulled in and it hits the sun, then the speed of it could be escape velocity if it was going the other direction.
Oh, yeah. Yeah, I don't think you'd be able to tell.
Okay.
Yeah. Like what we just read about on Space Weather News, that, there was a CME that came off the sun. Now, what if you watch that in reverse? And you watch this big mass of gas fly in and hit the sun and cause an explosion.
Yeah.
Would it look right? Probably.
Okay.
Some of it might look weird if you were able to look closely.
It's just weird.
Okay. So the law of gravitation is of such a kind that the direction does not make any difference. If you show any phenomenon involving only gravitation running backwards on a film, it will look perfectly satisfactory. You can put it more precisely this way. If all the particles in a more complicated system were to have every one of their speeds reversed suddenly, then the thing would just unwind through all the things that it wound up into. If you have a lot of particles doing something and then you suddenly reverse the speed, they will completely undo what they did before. This is in the law of gravitation, which says that the velocity changes as a result of the forces. If I reverse the time, the forces are not changed, so the changes in velocity are not altered at corresponding distances. So each velocity then has a succession of alterations made in exactly the reverse of the way that they were made before, and it is easy to prove that the law of gravitation is time reversible.
Okay, so he is saying that even if you took the impact and you reversed it, it would be fine.
Yeah.
Wow.
Yeah.
That's cool. Huh.
But that's just with the gravity.
Yeah.
Right, yeah.
Not the thing flying to pieces and all that kind of stuff.
Yeah. So the law of electricity and magnetism, these are time reversible. The laws of nuclear interaction, time reversible.